and what are the key issues, what are the key ideas that can be useful in this sector. Okay, so let me start with the introduction of the Internet of Things. So what is Internet of Things? With the advancement of information and communication technologies, each and every device in the network can have the information and information sharing and communication capabilities. Thus, we can assume that all these devices will have the capability to communicate with each other through a network configuration. And thus, we can have a ubiquitous connectivity among all these devices, which brings us to Internet of Things. So this lies on the basic pillars of the identification, sensing, communication, computation, semantics, and services. So Internet of Things have revolutionized a lot of sectors, including smart homes, healthcare services, smart metering, industrial automation, and so on. And it goes without saying that Internet of Things could be highly relevant to smart energy systems. So why we're saying that this is a smart energy systems? As we know that in traditional energy systems, we have generation resources, then transmission system, distribution system, and then at the end, we have the end users. But nowadays, the generation is not only limited to the centralized generation. We are also having distributed energy resources at the end users. So the traditional power system is also changing. And in this scenario, there will be more complexities added as the energy demand is growing, the diversity is growing. So when we have the information exchange among all the components of these traditional energy systems, such as through these control centers in the transmission and distribution network, and also better monitoring of the end users through smart meters and other automation devices throughout the network, then we can have these smart energy systems. Smart energy systems can achieve better coordination among these different components of the smart grid of the power and energy system. So the communication network goes side by side with the energy network. How can IoT be beneficial for smart energy system? Because IoT can enable this two-way communication, which is the key point of any smart grid network. And through this two-way communication, it can allow better visualization of how your energy demand and how the energy generation for the overall network is going on, better monitoring, and obviously more efficient of operation of the overall power and energy systems. This is what I could see that IoT can offer for a smart energy system. This is a snapshot of the visualization platform of the Deakin microgrid. So through this visualization platform, we can see how much generation and demand is going on at a certain time instant. I took this snapshot this morning. So at that time, there was plenty of solar generation, and we could also see the demand and everything. So with this IoT, what we have like intelligent devices connected to the connected to each of the buildings, and these intelligent devices can monitor how much generation, how much demand, how much is the power flow happening in each direction, and as a result, it can export this information to the cloud platform through which anyone can see, log into the cloud server and can see how much generation and demand is going on, and also like monitor the data for over 1 year, 2 year, and different insights can be driven from there. So there might be a question like, why we need IoT when we have the traditional SCADA systems? So if you already know what SCADA is, that's fine. If you don't, then SCADA is the supervisory control and data acquisition systems. which is the traditional way to monitor information in any power system plant, such as in a generation plant. There will be different processes going on. For example, there could be different meters which measure how much is the gas pressure, steam pressure, and so on. And based on those measurements, there are different programmable logic controllers, PLCs, which makes different decisions and change the and send different control signals to the actuators to change the operating set points and so on. And then for the overall monitoring, there is a HMI, human machine interface, where there is an operator who can see what are the things going on and can perform more higher level decisions. For example, generation, how much generation needs to be dispatched and so on. So in a traditional SCADA system, you can see everything, everything goes on within the plant and it stays there. Nothing happens out of there. So what will happen when we have geographically distributed resources? Nowadays, for example, if I take this example in Australia, let's say that there is a generation company which is located here in Victoria. Let me just bring the laser pointer. So let's say the main operations office is here in Victoria, and the company is now installing another generation resource in Northern Territory, which is around 4,000 kilometers. So you can see that these locations are far away from each other. So what could be the option for this generation company? They can have a control center built there, here in the along with the generation resource, so that there could be proper monitoring there and someone can take action based on if there is something going wrong. The issue with this will be the cost and the flexibility. The company needs to invest another building there and needs to employ someone there to be monitoring the equipments and monitoring the overall plant. So there could be these kind of issues. And if something goes wrong, then they have to wait for that person to report back to the operations center. And you can see that this is not as cost effective and as flexible, and it is not automated, the most importantly. What could be another solution which many companies are now looking at? If they can have this remote monitoring remote monitoring feature with this generation resource, and based on that, those information are sent over the cloud computing platform, and through the cloud computing platform, these operation center, they can also monitor what's going on, then that could be a feasible solution for everyone. We don't need to have different monitoring centers at different locations, different control centers at different locations. Rather than that, the control operations can be more coordinated. So we will definitely have SCADA over there, but then the monitoring and decision making mostly depends on this information that we receive from the cloud platform. So that's where the IoT can add a new feature to the already existing monitoring system through the SCADA. And as we all know that for smart energy applications, communication is a key requirement. And when it comes to the communication, then we need to think like how frequently we are receiving data and how what is the resolution, how much data we are receiving from these different components of the smart energy system. For example, if you look into this application of phasor measurement unit. So what is a phasor measurement unit? It's nothing but a meter which can monitor the current, voltage, these signals or in the distribution or the medium voltage or low voltage distribution network. So these phasor measurement units, they monitor these signals and they send these signals to the local phasor data concentrator, And the local phaser data concentrator can then send this information to different cloud platform. And from there, the central PDC or phaser data concentrator can coordinate this information and based on that, make intelligent decisions. So here you can see that we can have cellular communication for information exchange in this kind of scenario. As you can see that communication is vital for any smart energy applications. More communication can give you more data. So if you want to have data analytics for your smart grid system, you definitely need to have IoT so that you can get the data, the communications, and more information out of there. But what data can do? Why we need high resolution data? So this is an example where a transient event has been tested in Lawrence Berkeley National Laboratory, where a transient event is detected by the PMU, which detects 120 frames per second, whereas SCADA, it monitors every 2 seconds. So you can see from this graph that though there is a transient event, the SCADA is unable to detect that because by the time it comes to record the next measurement, the transient event was gone. But PMU, it could monitor that event. And based on that, it can provide important insights to the operators. So that's where the benefits from data come in. And for that, we need to have a proper Internet of Things technology, which can communicate the required information. So how IoT changes smart grid? So in the traditional smart grid, we have like field devices such as smart meters, PMUs. And for control operations, we will have remote terminal units or PLCs. Then for the overall monitoring, we have SCADA. For example, the EMS, Energy Management System dashboard. Those can be the higher level monitoring. Along with this smart grid, if we have now IoT enabled smart grid, what additional things we will have? We can have different smart end devices, which are monitored through different home energy management system. And this information can be then combined in the data fusion center, which can then forward it to cloud data center. And overall, all these information can be combined in the computation processing and analytics platform. In that way, IoT can augment the already existing monitoring through the SCADA system. So this will be the typical IoT architecture. At the bottom layer, we have the edge devices, the end devices. There could be billions of such devices. Each and every appliance of your home could be one edge device if you have some kind of smart plug or other communication module associated with it. The next level is the fog layer. These can be thought as aggregators or gateways, which can combine the information from these edge devices, and based on that, it can perform some computing to better coordinate the operation of these edge devices. Then at the top layer, you have the cloud computing platform, the cloud data centers. So the hierarchy goes like billions of edge devices to millions of fog nodes to thousands of data centers. What could be the potential applications of IoT in smart energy systems? It could be used for automating the generation. For example, let's say based on the load demand value, the cloud server can send information to this IoT device, which can compute the governor point, which based on which this generator operates. Then there could be like irradiation information, which will be available to this cloud server. And based on that irradiation information, the cloud server can compute the optimum alignment of the solar array for a certain location, and it can send that information to this IoT-enabled controller, which can then align this solar array accordingly so that maximum solar energy can be extracted. IoT can also be used for distribution networks, electricity distribution networks, where let's say we have IoT enabled phasor measurement unit, which can monitor when there is a load change in the system, the voltage current changes, and based on that, it sends information to the cloud server. And based on this information, the cloud server then compute how the tap change transformer should change its tap value and operates it accordingly. The more popular applications of IoT will be in the customer premises at the end users, because at the end user level, these IoT applications can do really amazing things. For example, let's say each of the appliances in the house, if they can be connected with a smart plug, they can forward this information to the IoT enabled energy management system at a house. And based on that, the energy consumption information can be forwarded to the cloud server. Based on that, the cloud server can compute like how efficiently the house is working compared to other houses. And also like it can send some switching command. So for example, there could be certain apps in the customer's phone using which they want to turn off a certain appliance. Let's say someone has forgotten to turn off the air conditioner at their home, and they want to turn it off remotely. They can send this signal from their cell phone, and then that information goes to the cloud server. The cloud server then sends a switching command to this EMS, and which then turns off the smart plug and turns off the appliance. Similarly, another application could be, let's say that there is a house which has excess renewable generation. And then this information can be sent to the cloud server, where the cloud server can compute whether there is an energy sharing opportunity with the nearby houses or not. Also, if there is demand response application required from that house, the cloud server can send a real-time pricing information, where the cloud server can be aided by the utility. The utility can compute a real-time pricing signal to change the demand, energy demand of the house, and based on that, the cloud server sends the information to the customer, who can then change their demand to match with what is required by the utility grid. So for disruptive applications in energy systems, such as peer-to-peer energy trading, Internet of Things technologies will be very much necessary, where you'll need more and more information exchange among each of these participants. So what is peer-to-peer energy trading? We can consider that if there are a number of houses with solar panels and battery storages, some of them might have excess generation at a certain time, while some other houses may have energy deficit. And when these two groups of houses, they coordinate with each other, they can satisfy their supply demand balance locally, rather than selling to the utility grid or purchasing from the utility grid. So that's the concept of peer-to-peer energy trading. As you can see in this figure, there should be a huge amount of information exchange happening from these participants with the EMS, so that the energy sharing can take place, the financial settlements can take place in a proper way, in a beneficial way. So in these kind of applications, IoT can definitely make a big impact. Other applications could be IoT-aided appliance monitoring. So let's say that you have a certain number of appliances in your house which are connected with smart plugs. And based on that, you can monitor the energy consumption information. And you have a home energy management system enabled with edge computing. Now, let's say you have a faulty appliance, which is consuming very high energy. And based on that, your HEMS detects an abnormal energy consumption pattern. Then it compares with the appliance signatures. It uses the data disaggregation techniques and find out which appliance is causing that abnormal usage. And then reports to the customer that your electric motor may not be working properly because it might be shorted and it's consuming over all 24 hours, things like that. So that could be a very important and useful application of the IoT, which can save money for the end users because they have a better idea that their appliances are not working properly, and it's also useful from the safety perspectives. Another application could be IoT-aided demand response. So let's say this cloud server, it has the information about the weather forecast and historical load demand. And based on that, the cloud server can compute what should be the predicted demand and predicted generation for the next day and sends this information to the HEMS. This HEMS is also enabled with edge computing facility. And then it has the information of how much solar energy will be generated and how much will be the load demand. Based on these information, the HEMS can use data analysis and optimization tools. And based on that, it can compute the useful demand response strategies. How effectively the end user can reduce its demand or shift its demand so that it can reduce the energy cost. For example, the HEMS can compute some strategies like don't operate your washing machine between this hour and that hour because there is going to be a rain during this time, so you are not going to be able to dry your clothes. Or it can also send an information to the customer that how about you change your temperature setting of the air conditioner to this point for this amount of hours. So for example, if you want to change your temperature settings of the AC to, let's say, 19 degrees Celsius between 1 p.m. to 3 p.m., because at that time you have plenty of solar generation and you can reduce your energy cost because then you don't need to turn on it again at the same setting at 5 p.m. or 7 p.m. when the energy cost is much higher. So things like that can be reported to the customer, and based on that, the customer can take actions. Or this can also be automated if the customer has an IoT-enabled device. So in that case, the HEMS will be able to automatically change the setting of the AC, IoT-enabled AC, so that the energy cost can be saved at the customer side. For the distribution network, applications could be fault identification and restoring the network when the fault is cleared. Typically in the distribution network, auto reclosers are now used. So this is a type of circuit breaker, but the benefit is that it keeps sensing that circuit, and whenever it sees that the fault current it is low and the fault is not there, fault is cleared, it automatically recloses. It doesn't depend on someone else to go there and change the setting. So that's how the reclosers are being used in the distribution network. Now let's say you have the IoT enabled PMU, the phasor measurement unit, which has also the edge computing facilities with them. Now assume that there is a fault occurring in the distribution network, And as a result, this recloser 1 opens. Though this recloser 1 opens because of this fault, there will be changes in other parts of the network as well. And this PMU with the recloser 2, they should also be able to sense that there has been some changes based on the common pattern of the voltage and current signals that is stored at them. Then based on this information, it can identify whether that change is still there or it has come back to the normal state. And it can communicate with the other PMU that the recloser should not reclose because still there is a change from the normal condition. So the chances are very high that the fault is not cleared yet. So in that case, the recloser 1 does not have to check again and again by closing that whether the fault has cleared or not. So these type of applications are possible when you have IoT in the energy systems. IoT protocols, how these nodes are connected with the web applications in the IoT network, as we have mentioned that there are end devices which are the IoT nodes. These IoT nodes will have very less amount of data, few bytes of data, and then they are connected through the IoT backhaul through the router, which can carry more data, let's say hundreds of bytes, and then it goes to the web application where we have the typical HTTP protocol and TCP over IP protocol where we have more data gathered. So what are the typical protocols, the popular protocols that we use for IoT applications? In the application layer, we have the MQTT protocol. This protocol is used at the application layer. If you are aware of the OSI layers, then we will mainly talk about the physical layer or the network layer or the application layer when it comes to the IoT devices. So on the application layer level, it's MQTT, which uses publish subscribe protocol. And this protocol is used because it is open and lightweight. Lightweight protocol is very important for IoT because there is significant constraints on the network bandwidth, and also there could be intermittent communication. Due to this, the MQTT protocol is one of the most popular solution for the IoT applications. This uses a publish subscribe protocol, which has 3 components: subscriber, publisher, and broker. So subscriber is any device who has a list of any device who is interested to receive a certain topics, and it informs those topics to the broker. So it subscribes to those topics. And the publisher is the generator of information. So it publishes the topic and information, gives to the broker. And the broker then works like the middleman and achieves the security by checking authorization of the publishers and subscribers. So it matches the topic and information that is given by the publisher and that is requested by the subscriber. On the physical layer, that is when it comes to the communication channels, when it comes to the communication signals, there the protocol is typically low power wide area network protocols, because these technologies are suitable for low data rate applications, which can operate over a wide range. The data rate ranges from 0.3 kilobits per second to 50 kilobits per second per channel, and the operating range could be few kilometers in urban area and over 10 kilometers in rural settings. The benefits of this low power wide area network technologies are they are optimized for power consumption, and they can run on small inexpensive batteries for up to 20 years. There could be 2 categories based on the spectrum usage. One is the unlicensed category, under which we have LoRa and Sigfox, that is the ultra narrowband protocol. The other one is the licensed spectrum usage, under which we have narrowband IoT, which is actually published by the 3GPP group. So what are the typical features of these low power wide area network technologies? So if you look into the LoRa technology, it uses spread spectrum modulation, and it uses orthogonal spreading factors to separate the information. The UNB ultra-narrowband technology from Sigfox, they use frequency shift keying and frequency hopping. On the other hand, narrowband IoT uses orthogonal frequency division multiplexing, or OFDM technologies. These low power wide area network technologies, they often use repetition for reliable information transfer. So if the information cannot be received by the receiver, it keeps sending it again and again. So all these low power wide area network technologies, they have a limitation, common limitation, which is the limited bandwidth, because these have to operate over the regular communication channels, the regular communication services. So there cannot be a significant amount of bandwidth allowed for these applications. When it comes to the IoT architecture, we need to consider a number of things, like how these end devices are going to be connected and how this communication will take place. Let's say this in this case, we have all the IoT end devices sending information to the cloud server. So basically these end devices, they just send their measurement signal to this cloud server, and all the computing, optimization, decision-making, analytics, everything happens here in the cloud server. And end devices cannot make any intelligent decision. We do have this kind of structure, this kind of architecture. It makes things simple because like the end devices, you're just sending information, just communicating, and there is no need for additional processing power, computation power. So it's good for that perspective, but does it really achieve the goals of the Internet of Things? How scalable will it be? The existing cloud computing platform will say that, yes, they can handle lots of devices. Maybe it's true. Maybe they can handle 1,000 devices, maybe 1,000,000 devices. Billions of devices? I don't know whether they can handle it or not. They may or they may not, but eventually that will require a lot of resources, even if they try to handle these through a lot of cloud data centers. Now let's think the other way around. If we do not push all the things in the cloud, if all these end devices, they take the responsibility that they will have all this intelligent decision making and they will operate completely autonomously. So in this case, they will have to communicate with all the other devices through an IoT gateway. The IoT gateway can increase that operation range, the communication range, but all these devices, they take these decisions by themselves. The problem that will happen here, there is no overall monitoring here. So if something goes wrong, there is not a higher layer from which we can say that how these devices should coordinate with each other. And there is a risk that we will end up with islands of automation. This was a concept of 1980s when there was different automated components, and there was no communication between those automated components. So here, though we have the communications happening among all these devices, but how can we ensure the coordination among these devices if we do not have any kind of overseeing the network? Also, there will be issue with supporting the communication bandwidth and interference issue if you have millions of devices communicating. So what could be an architecture that can address both issues? Perhaps this one, where the IoT end devices, they have some capability to make local decisions using edge computing. And they send those information and decisions to the IoT gateway, which coordinates and optimizes the operational strategies using the fog computing. And then we have the cloud server, which oversees the network and makes some higher level analytics and coordination. This might get the benefit of both the cloud server and the distributed computing resources through edge computing. However, which option will work better, that will depend on the application, how we want to extract the data and how we are going to use the data. Based on that, how are we going to optimize the information? Everything will be depending on that. One example could be the appliance control in a smart home. Let's say you have these appliances with the smart plugs connected, which sends the energy consumption information to the HEMS. The HEMS has the edge computing capability. And based on that, it can compute what is the best time for turning on the appliances. On the other hand, there is a central energy management system, which is connected to a number of houses. And based on that, based on the information it receives from individual houses, it optimizes the utilization of renewable generation for those houses and also computes energy sharing strategies for them. And let's say we have the cloud server there, which can compute and coordinate the demand and generation forecast. And based on that, it sends the information to the central EMS, which computes the strategies, and then it sends this information to the HEMS, which computes the strategies for the local level for the specific house. So this can be an example of the architecture that I mentioned before. So when we talk about the IoT technologies, we need to keep in mind that there are different requirements which we need to fulfill if we are going to enable IoT technologies in smart energy system. First of all, what could be those communication requirements? It has to be reliable. It has to achieve low latency. If you need to satisfy some energy system operation within a very short period of time, you need to have the information exchange happening before you need that operation to happen. So you need to think about like how often you need to control the system. Is it like every minute, every second, every millisecond, every hour? Based on that, this latency requirement will change. The ability to multicast is another important thing, because there could be multiple sensors sending the information to a gateway. How these multiple information streams can be handled. If the multiple information streams can be handled without interference cancellation and through the use of any multicasting technology, that will be best use of the spectrum resources. Interference management is another important issue, because there will be definitely interference from other applications, other cellular applications. And if the technology is using the unlicensed spectrum, there could be more interference issues. Energy consumption is another factor. The energy consumption of the communication technology. How does the battery perform? Like how often does it have to sense the information, and how often does it have to communicate? Based on that, the battery life will vary, and the energy efficiency of those communication technologies, that will be an important consideration. However, the most important and the most significant requirement that these IoT technologies will have to ensure is the security, where everyone is still having some concerns whether these technologies are able to achieve the security requirements that smart energy systems need or not. What could be the security issues? Many of these IoT technologies, they have repeated data transmission method. So whenever the information is not received, then these devices, they just send information again and again, which means that the signals now spend more time in the air. As a result, it becomes more susceptible to attacks. Also, many of these protocols, they use a number of spreading factors or frequencies to evade the attacker, but it could be limited number of spreading factors and frequencies which these days attacker can detect, attacker can already decode because of high computational power. Also, there could be limited resources available for complex security algorithms. So ultimately, we have an increased ability of attackers to breach privacy and security. So this is definitely a shortcoming of the IoT protocols, and proper standardization and proper security mechanisms definitely need to be incorporated before IoT technology can be properly integrated with smart energy systems. However, we should never think like the person here who said that to make the system secure, he turned off all the devices. So that's definitely not a great way to deal with the IoT security. So what could be the best way to integrate the IoT technologies? That's still an open question, and you might come up with brilliant ideas and thoughts, which I would definitely love to hear. So here are some references which I have used, which I have found valuable to prepare this presentation. I would like to thank you all again, and I'm happy to take questions.
Thank you so much, Shama, for the really wonderful presentation and very thought-provoking presentation. We had a huge turnout today. More than 100 people are still here. I think we can go in the question and answer session. So let me firstly allow everyone to unmute. So if I ask you to unmute yourself, then you can unmute and then ask the question. So I think first question, yeah, the first question was asked by Dr. Muhammad Ahsan Zami. So if you could unmute yourself and introduce yourself before asking the question. Yeah, hi, can you hear me? Hello.
So if the question is posted in the chat window, I think you can.
Yeah, I can read it aloud. So
Yeah, because there is a lot of questions. I'm finding it difficult to follow. So which one I should?
okay, Dr. Ahsan Zami asked that the research on IoT-based topics require data. Is there any publicly available database where one can use the data for research purpose? As often the data is not readily available.
Yes, obviously the availability of data sets is a very big issue, and we often talk about these things like how better we can have the data. So yes, obviously there are publicly available data sets. You need to look for it. It might not be like very high frequency data set because let's say if the number of let's say you're taking measurements every millisecond or every second, you can imagine like how much data will there be. It will be hundreds of gigabytes of data, and whoever wants to publish that data needs to use a lot of cloud storage, and they're not going to give it for free. There's the issue. However, if that's not the case, if you're just wanting to use the dataset for energy system, typically smart meter datasets, these are readily available. I have seen the datasets from, I think, AEP, the American Electric Power. There are some datasets, and I have also seen some datasets from Osgrid, which has smart meter data. So yes, there are data sets available, but depends on which sort of data you are looking for. And it's always possible that if you're planning to do some research, you can create your own data set if you have the resources to do some kind of experiments, for example, monitoring temperature and this kind of information, yes, that you can that could be another possibility.
Thank you very much. The next question is from Shipul Kumar. So the question is, you said that when we want to turn off any appliance for its misusing the energy or abnormally working, but then we talk about the grid system, but how can we turn off the misusing energy system? Could you explain it briefly?
So that turning off appliance, that application, what I wanted to say is like using the data from the captured from the HEMS and the computation done through the data disaggregation, we can identify which appliance is faulty, and based on that, we can inform the customer. So we cannot, and we shouldn't really turn off the appliance without informing the customer, because then the customer might think it's a breach of their privacy, because it's their data, so they should take that decision. However, there can be other concerns that if it's a security issue, then yes, there should be some control available at the utility to turn that off. But to be honest, because the privacy issues are much more significant here, typically the customer will be informed about it, and the customer can get this information from their HEMS using a text message or something, and then based on that, they can take precautions.
Okay, I have a related question regarding this. So when we are talking about a man-in-the-middle attack or a spectrum level attack, but suppose if a device itself is rigged so that it's giving falsified data to the utility, can this be also mitigated somehow? Or, is this something that's being researched on?
Yeah, definitely there are researches going on, and honestly speaking, I'm not doing the research on the IoT security side that much, but definitely there are security protocols which can be used there, and definitely these are some of the shortcomings of using IoT. Like if it is giving falsified information, how you identify it from the aggregate information. Yes, that's definitely something that needs more research.
Thank you very much. Next question is from Amandeep Singh. So his question is how IoTs can benefit the water industry. Is there any work going on there?
I have not explored that much on the water side, that how the IoT devices are being used there. But I know that you can have like monitoring units there as well. So because IoT depends on the information collection of from the different end devices, I believe that IoT can similarly used in water industry as well. I have seen some work where the water pressure and similar other parameters are being monitored, and based on that, some decisions are being developed by a management system which can show to the customer that whether they are using too much energy and which application in their home, like whether is it the regular water usage or the toilet water usage that is using more water. So those kind of information can be revealed using the data. But it again depends on what sort of sensors, what sort of monitoring equipments you have available.
Okay, thank you very much. Next question is from Midhat Mahbub. So I don't know if you're familiar with the Bangladesh power sector. So what's the future of IoT in the power sector in Bangladesh? What about the Rupur nuclear power plant or its stability? Can IoT somehow benefit those things?
IoT definitely can benefit the power plants, including the nuclear power plants, because it allows you to do more monitoring and better decision making. So I would definitely say that there is scope for IoT in any modern generation systems. So even for Bangladesh, there is scope. how much investment will need to be there, and how feasible it is, that's a separate concern, and that needs more policy level decisions rather than research level. So that's what I can say.
Okay. And thank you so much. Last question is from Akib Mahmood. So his question is, what are the top companies presently working on IoT application?
If you're talking about Australia, there are different organizations which are working. I personally work with one company which is called the Itron. They have their branches in different parts of the world, including US and Singapore, UK, different parts. So I'm working with them in some projects to develop the IoT solutions for energy systems. Other than that, yeah, there are other organizations. If you search for the IoT Alliance group, you'll find more information of which organizations are there supporting these kind of initiatives.
Okay, thank you very much. So next question is from Engineer Muhammad. He's a member of the Engineers Institute of Bangladesh. So the question is, how much time it might take to include IoT in the Bangladeshi power system? So do you know if someone is working on it, or what's the current trend?
I have heard, I have definitely heard some people were talking about the IoT, but they're mostly from the telecommunication sector. I think it still needs some time to come to Bangladesh, because I think lots of developments are happening, and it might still need time, and everything depends on how much is the demand for that additional information. If there is really some scope for using this additional information to improve the capacity, improve the generation of the power plants, yes, that will be definitely a near future. But if it is the case that we still have we still don't have enough control over the network, then I think that's a different story. So I would definitely say that it's high time that we should start thinking about it, how we can incorporate these, because there will be a certain point when we will want to have the data analytics incorporated for improving the power system operation. And then we will definitely need more data, more information, more communication. So there should be some concerns before, there should be some considerations before setting up even a new power system asset, that how we can integrate these kind of IoT technologies, how we can achieve more reliability through this information sharing. So there should be those kind of considerations.
Thank you so much. I don't see any other questions in the chat box. So I would like to invite everyone to turn on your webcams. We would like to take a group photo, virtual group photo with the speaker. And while you're turning on the webcams, let me quickly share my screen.
Yep, then I'll stop sharing here.
So thank you. This is a virtual certificate of appreciation. So we're really glad that Dr. Islam has taken her valuable time and prepared this wonderful presentation for the young professionals of Bangladesh section. So we would like to acknowledge that, and we prepared this certificate of appreciation for her. And hopefully after the session, we would send out the certificate to her.
Thanks a lot.
Thank you. And let me stop sharing as well. So right now, if you're comfortable, please go ahead and turn on your webcam. We're going to take two screenshots of the two screens. So here goes one. Oh, so there is another comment, a couple of comments regarding the recording of the session. So if we have done a recording, so I'll then privately first share the recording to Shama. So after that, when she approves the recording, if she approves it, then we would make it public, and then publicly share it using our YouTube channel and Facebook page. So page 2. Okay, so that was both of the pages. So thank you so much everyone for joining the event. So on next Saturday, we have another event. We are bringing Mr. Nadim Chaudhuri. He also was a former faculty member. So he's a current faculty member of BUET, and he's currently doing his PhD in MIT. So he would be talking about his current research. And on behalf of the IEEE Bangladesh section and the IEEE Young Professionals, we really appreciate that all of you who came and attended our session. And especially we give thanks to the speaker, Dr. Shama Naz Islam, for her wonderful presentation. So with this, I thank everyone and conclude this session.
Thanks, everyone. And if you have any question, you're always welcome to send me email. My email address was shared in the presentation slides, and you can also communicate with Sajid to get my email address from him. Thank you.
Thank you.